specifics of that question, if I recall. So
Excuse me, Professor. May I ask a
yes,
question?
yes.
I downloaded the Excel file for the two material flow, and it wasn't the last version that you
Oh,
actually
okay.
shared.
Thank you for reminding me. I'll have to to update those. I have also updated, and we'll look at that later. I have uploaded a couple of macro books, one for Excel, the other one for LibreOffice. And I'll go over later how to use them and what I made them for. But it's for the second part of the what I want to show you today. So, but thank you for for reminding me. Yes, I do have the other sheet. Um, so a strip footing with a width of 2 meters imposes a stress increase of 50 kPa at the surface of a uniform clay layer that is 8 meters thick. And the question requires us to find the pore water pressure, excess pore pressure, right? Within the clay layer. So if the question is after 15 years, um, where we have a CV, let's make sure that we have proper dimensions for this. A CV of 1.10 meters square per year. Okay, so first have a look at the data that we had generated. So last time, if you will recall, we had calculated delta and beta, correct, and generated the using the equation for using Boussinesq, basically Boussinesq equations. We had used this geometry, and under a strip footing, you could use this basic geometry here to estimate the stress. It obviously assumes an elastic medium, but this is all part of Boussinesq theory. So last time, I think that's what we had worked on, correct? And we had generated this spreadsheet. And based on that spreadsheet, we were able to look. So this is a symmetrical plane. We were using symmetry to reduce the number of calculations we needed to do, right? So this is the axis of symmetry on the left side here. And so the footing ends exactly at the edge there. Okay, and so we go from 0 to 8 meters of depth, or if we looked at in terms of contour lines. Again, this numeric is a nice little application. I from all the spreadsheet software, I mean, NuPlot gives you the all the flexibility you want in plots. But if you want to stay within the domain of a spreadsheet, you will definitely get the best plots using this little piece of software. It's very powerful. On the same plot, you can also stack different kinds of plots. You can have an XY scatter plot with a contour map, so you could combine all kinds of data plots on the same image. It's extremely flexible. I mean, maybe that's something I should do one day, is just make a little video to show you the plotting power of this little tool, but I just love it. It does lack macro utilities. That's the one weakness it has, but it has very good statistical functions. Of all the spreadsheets, it has been developed with that in mind. So if you're doing a lot of statistical work in your research, it's probably a tool that you would like to have. Also, as I hover my mouse around here, it gives me some coordinates of the points, which is pretty cool. I don't think you see it on screen, but it's something that I see with my mouse here. So this gives you an idea of the plots, and if we look just say under the center, so the blue line that we see here, that the stress distribution under the center of the, let me increase a little bit, maybe the thickness of the line, so there. A little bit more visible on screen, I think, would be best. Like this. Okay, so I just wanted to represent stress distributions because we're doing a 1D settlement analysis right now, right? So pore pressure dissipation. And so what we want is only to get the data from under a specific point. So most likely we'll use the center because that's where the largest amount of pore pressure, excess pore pressure is present at the beginning. But you can see its variation at so the pink line is the edge, and the green line is I believe a meter out of away from the footing. So just to give you an idea of what the stress distribution is with depth. And as you notice, as you get to 8-meter depth, even 1 meter away, you have a similar increase in pore pressure as you had directly below. So as you move away, it does increase. You have a spread of the pressure. Actually, this is best illustrated from this figure here, where you can see same pressure distribution, but this time is with the position X. Again, let me increase the size of the thickness of the lines so that they're easier to follow. Okay. So this time we have a different depth. So immediately under the footing we have this sharp. Obviously we have at the footing, directly below the footing, we have the full application of the 50 kPa stress, and then 1 meter down we have a reduction, but also a spread, and that's the key here because you have a distribution in an elastic medium and you have Poisson's ratio. You do have a spread of the stresses going down with depth. So what we're interested in doing now is going back to our 1D consolidation analysis, and this particular case, let's have a 1D. I will insert a new page, and this is 1D consolidation. Okay, so for 1D consolidation, we can have at various depths. Let's see how. Here we were going at 0.1 meter all the way to 8 meters. It might be a bit too ambitious, but let's do it for now. So let's just take this information from here. Okay, so we have our depth of interest. Delta Z is 0.1, and we'll consider just under the center of the foundation. So I just want the values for now. Okay, so we have our delta Z, and we have our initial pore pressure dissipation. Now we are saying that we have dual drainage, so that's one of the limitations of the 1D analysis, right? Because in 1D we have to assume that although we have a finite size to our platform, to our footing, we are assuming in 1D drainage that water moves straight up, but in practice, if we have a sealed, so good contact here, water actually has to bypass the footing, right? And so that's why ultimately we'd rather use a 2D consolidation solution, so that we would be able to model the path of water like this. Also, what the 2D consolidation model lets you do that 1D doesn't let you do is that you could conceivably have a clay, a relatively uniform clay, but that it might have little seams of, say, silty material like this that increase enormously hydraulic conductivity, but in the horizontal direction because it's very thin, and so there's no obvious addition of hydraulic speed of consolidation vertically, but because water can leave through here, okay, you could have much faster dissipations of pore water pressure. So those are all the little intricacies that make 1D consolidation limited in its scope in predicting the time rate of consolidation. Okay, but say, okay, so but let's finish just considering our example for now, and we want to consider the material properties that we had, right? So we have CV. So we have CV is equal to 1.10 was it meters squared per year, and the question, let's go back, 1.10 meters squared per year. Okay, we have a Q naught of 50 kPa. We have a width of our footing is 2 meters, and we said in our case we are using delta Z is equal 0.1 meter, and the initial applied stress is equal to 50 kPa. For our little example. So this is what, so in our case we did not just distribute it with depth, we did the distribution in 2D, but we were only interested in the distribution under the center of the footing, and that's what we get in our little spreadsheet. And this column is the excess pore pressure, because initially the pore pressure carries all the change in total stress, right? If it's only over time that the effective stress will carry that change in stress. So initially we get this this change in pore pressure with depth. And so with our 1D consolidation equations, what did we get? So we ended up having u at time t plus 1 minus u at time t is equal to CV delta t over delta z squared, and we call this R times u all at time t minus 2u at time t, so that's I minus 1 I, and that's at position I, plus u I plus 1 at time t, right? Something like this. And so we were able to, using the explicit method, which we can use right now. It might be a little bit simpler, although we could use any of the methods we have seen at this point. But let's stick with the explicit, so we don't have to invoke a matrix or build the matrix. So we had r ui minus 1 plus 1 minus, so at t plus 1, 1 minus 2r r ui plus 1, right? So that was the general equation we had for this kind of problem. And so we therefore have to determine what r is. And in this particular case, we said that it's 1.10 meter squared per year. Our delta t, well, we want to know what delta t is. First, let's assume that it's 1 year, just to see if we're within the parameters. And we know that delta z is 0.1 meters. So we make that squared, and that gives us 1.10 times 1 divided by 0.1 squared. So 110. Would you say that that's too big or right size? What's the maximum R we can have? Can you guys still hear me?
Yeah, Professor.
Okay. So what's the maximum value of R we can have for the explicit method? I recommend using it as a guide even for the other. R must be smaller or equal to 1/2. Okay? So 1/2 equals to 1.10 meters squared per year times delta t. So we have to figure out what's the maximum delta t we can have. It's going to be very small with the delta z we have there. Probably we should have used delta z of 2 meters if we wanted to be able to reach those 15 years, but let's play it by ear for now. So 0.10 meters square, so delta t will be equal to 0.10 meters squared over 2 times 1.10 per year, and so that will be equal to 0.00455. It seems to be periodic. Okay, and so that being the case, so if we were to so it's basically a day and a half that we need to reach our 15 times 265. That's about 5,400 would need in the count to get to our values. Anyways, we may not need to go to the end here. What we want to do first is do our little calculation to some degree. So let's see how it dissipates in this particular case. So we said that R was equal to 110. And so if we go back to the spreadsheet, we have a R defined. Let's define the value for R. No, it was 0.5, sorry. Right? So, right, assuming, oh no, maybe not 0.5 because let's, instead of using 1.5 days, let's just use a 1 day plain. So in this case, R will be 1.10 times 1 over 365 0.10. Okay. So that gives us a value of 0.30112. 0.30112. 0, 1 or 1, 6. Okay. 30116. That sounds like a plan. And so we can now calculate our values. So we have R times the previous one plus 1 minus 2 times R, the previous one at the same node, oops, B3 plus R times the following one. So that's 1 day in each I'm just typing a name here that will be obvious. So U1 and at the boundaries, because we are assuming double drainage, at the boundaries we get 0, right? So we have our boundary conditions and our name. So let's go far a bit. We're getting close to 1 year. Now I'm keeping every single day of our simulation. So let's go for 365 days. Okay, so if I copy this, and in theory every time that I paste now, I have added 1 year. Right, so if I paste again, so that's 3 years. Oh, we're going too far. So we cannot go to more than 2 years for now. We cannot have 3 full years based on the available sheet. I should have done it in rows, I guess, which I suppose I could still do. If you will give me a few seconds, let's do that. Actually, it might be, as I know we have a lot more rows than we have columns, right? So so let's just delete that. Okay, and we cut this, and we will, oops, or we will transpose, oops, as values. We paste as values, transposed. There you go. So we eliminate this, and we do the same thing with the other one. We paste as values, transposed. Okay, so we now have our values in rows, and now we can do the same, concatenate, and we just take a U, and we say, this time instead of column we say row minus row A2, and here we have at our boundary we said we had 0. Actually we had 0 even at the first boundary, right? And immediately after the test we already have the 0, and so we have here R times the previous plus 1 minus 2 times R times this node plus R times the following node in the past. So we did the same thing that we had done before, except that now we have it in rows, and we can copy this. We go to 365. Oops. Oopsie. Can I not insert rows? Yeah. Okay. We need to enlarge sheet. Oh, I see. Apparently, to save resources, there's a limited amount of shoot. So how do we insert enlarge sheet? I think I need to make a new sheet. Yes. This is because it's saved in Excel format. I opened it in Excel format, and by default it reduces the sheet size. So let me paste this. IV, and this goes to Okay, let's change spreadsheets for now. Let me close this file. And we will also, okay. And so we have our sheet. We want to obviously get at least our first year, so 365 and some. Oops. Oh, these were static numbers? I thought it was a formula. Oops. Let me redefine numbers then. So we will add R, which we said was 0.30116. We know that delta Z was equal to 0.1. Okay, and I will have to redo these calculations except for the first row. So this is row minus row A2. Okay, so that gives us the name of our formulas. And then we go to these values here, where we have to put again R times the previous node plus 1 minus 2 times R times the previous time but the current node plus R times the following node. Okay, so now we have 365, and based on this, what we want to do is repeat that 15 years if we wanted to have it 15 years. So 2 years, 3 years, 4 years, 5 years, 6 years, 7 years, 8 years, 9 years, 10 years, 11, 12, 13, 14, and 15 years if I'm not mistaken. So that's one way that we could do it. So we could take now snapshots in time to see where those sheets are. So if we were to take, obviously we want to have the depth, we want to have the initial excess pressure, and we could take say after 1 year, so 365, uh, 365, correct? say 2 years, so 730. $730. And let's go to our final of 15 years in this particular case. And if we now make a figure, XY scatter. Oh, I think we had the disconnection. Are we all back?
Yeah.
Okay.
Now we can hear you.
Okay. Let me reshare. We need XY scatter in rows. So 360. So these are the various chart elements. X-axis, that's depth, but we could change it soon. So let's finish for now. So we see here the variation of pore pressure with depth over time. So after 15 years, we still have some pressure, although it has been significantly reduced. Okay, and that's the profile with depth. Okay, so after at different periods in time. So we can keep this for now. Oops, did I accidentally remove the chart? Navigation. Okay. So let me save the file temporarily, so we get something to sun. This one is 1D and 2D consolidation. Okay, so that was nice, but first you saw that I needed a lot of rows, which you may just not necessarily want to do if you just want to go to a specific position in time. You might want to just save up on that, or you might want to be able to present it in columns and to have your data with depth in columns. There's different reasons that you might want to do it differently. So I have made, for this particular reason, I will make a duplicate of this, move to end position, yeah, 1D. I have made a little macro that all it does is basically copy and paste. Oh, did I copy? Oh, was not my real intention. I just wanted to add, but it will work. So if we, in this particular case, basically eliminate everything. But the first one. So that is the previous step. And now we can have the next step, right? Where we basically do the same thing. We keep our boundary conditions. And there we have, I can just copy this one from the previous one, yes. Okay. Hello, are we back? I think we disconnected again. I was trying to basically rebuild the, let me make sure I have the chat on. Okay. So I was saying that it's also possible, instead of generating all these tables, which works nicely in 1D, it becomes cumbersome when you have bigger, more and more nodes and so on. So we could, in theory, say, if I copy this and I were to paste special and just paste the values in the previous location, then automatically this row here recalculates. So I paste again, paste special values, bang. Okay, so I am now changing, and if I keep track of the iteration that I'm at, I can keep track of the value that I had. For instance, let's say that I go back here, I copy this, but instead of calling u 0, I just call it 0, and I say that this is that plus 1. Okay. So what we have now is, okay, we are now keeping track of our iterations, see? So if I copy this and I were to paste it there as values, okay, I'm updating this, and at the same time so I do my calculations, but I'm using less real estate, right? And I don't have to make a bigger and bigger spreadsheet every time, which, as you know, can become pretty heavy to use. And so I have made a macro to do these things, and say that we go back to 0 there, reset our initial values from the previous page for the 0. Say that I call this point the iteration index. Tools, macros. Okay, I need to have iteration source and iteration target. So my iteration source is this entire row, iteration src, and that single column I call it iteration tgt. So now if I try to run my macro, macros, run macro main. Okay, so what I get now is 100 iterations, because that's what I had set as my limit. So I could have a variable where I just keep track of my variables, and say I call this variable max iterations, and I just give it as a name. I call it iteration, I believe it's max iterations. Okay, so if I call this 5000, which one is the one we wanted? 5475, so we call it instead 5475. Then if I were to reinitialize things, add 0, pasting special as values, call it 0, and now I were to run my macro from iterative programming, it should in theory go up to 5475 and get the same value. So all that macro does is copy, paste. I tell it where to copy from and where to paste to, and that's what it basically is doing at this stage. Okay, so we'll let it finish its computation, and we should get the same numbers that we did previously. Okay, and now we have completed the calculations. So we should get there 0.071, so there's the same values that we had before. Right? I could have gone 1 year at a time and copied the data. So if I had my max iterations 365, I could have done that also and just kept the values. But let's have a quick comparison. I should have exactly the same thing that I have 0.7464. Oops, it's a little bit off. It should have been exactly the same thing for the same number of iterations. So 7, 4. Oh, we may have gone a bit further than I thought for some odd reason. Anyways, it might have come from rounding off at some point during copy and paste operations. Maybe there's some difference there, but you see the process, and ideally we would have about the same kind of shape in our stress distribution if we were to draw the figure now. Oops. Let's delete that one actually and redo this properly. Okay, so we have something in that order, which is basically what we expect to have anyways. So the shape is correct, and if we were to go to our maximum of 50, okay, that is basically what we'd expect it to have at 50 years. That's what we had in the figure that we had for the previous one. So that little macro, let me just start something to have a view at it. Let me connect to the student labs. I will just show you how the macros themselves work and how to install them. I have made one for Excel as well as one for LibreOffice. LibreOffice has some extensions that let you keep some records. I haven't had the chance to add that to the Excel one. I'm having trouble connecting to the computer labs, unfortunately, so we may have to drop that. Yeah, my connection is not good today. I'm not sure what's going on. It went very smoothly in my previous class, but for some reason it has can you still hear me, by the way?
Yes.
Oh, thank you. Okay. Yeah, I'm not sure what's going on today. Okay, so if you go to, yeah, no, the computer labs are still not connecting. Maybe if I go, Oops, I didn't want to do that. Okay. Remote apps. Maybe I can connect this way. Okay. Yeah, that's not gonna work. Okay, so I'll just let me log into Brightspace. I just want to show you at least how to where to access them, and I'll discuss how you would run them. I will have to make a separate document just to show you how to install it in that case, because this is really not working out. Oh, okay. If you can still hear me, then what I will do is just try to go to shortly through the macro. Let me do something differently. See if I can share at least my macro building. So document browser. We lost again the. So in terms of document, I need to chat. Properties. And so basically what I have is this macro copies from, so you need to define a variable called iteration underscore TGT in your document. So first you need an iteration index or iteration indicator in your document if you want to see the iteration that it has. If you don't want to see it, you don't need to define this variable called iteration indicator. But what you do need to define is two variables: iteration underscore src for the source, that's the entire range that will be copied at each iteration, and the area where it will be pasted. You just need the upper left corner with a variable called iteration underscore tgt. Then if you define a variable called iteration max iterations, that will let you, so you need to define a cell with that name. That works in either Excel with the macro for Excel or in LibreOffice. That one will allow you to reset the number of iterations that it runs before it stops. Okay, and all it does in the iterations is copy, paste, copy, paste, copy, paste. So all the treatment of the information, it's up to you to provide it by the formulas that you put in the spreadsheet. Okay, so those are the two values. Oh, sorry, you're not seeing the macro. Oh, there, you should see it. It did not change automatically. Thank you for pointing it out. So these are the variables that you need to define, these first two. Can I zoom in? Oh, did we disconnect again? Can you see the macros now?
It got disconnected, Professor, and now we can hear you.
You cannot hear me? Oh. Sorry, it went on mute apparently automatically when I was disconnected. So you can see the macros now?
Yeah.
Okay, so iteration underscore TGT is the variable you must define, as well as source. So TGT is a range. You select the area that you want to have copied, and iteration underscore src is one cell, the upper left corner, that you need to define. If you're running the LibreOffice macro, there's also keep records. So if you have a variable called iteration underscore keep records and it's set to true, then you define another variable called iteration underscore target range or TGT range, and iteration record src and record TGT, sorry, these two. And iteration interval, record interval, RC interval. So this is how frequently, so not necessarily every iteration will be recorded. So what it does is like the copy paste of the iteration, except that it will be in another range where instead of overwriting every time on top of the same target range, it will move by one row down. So it's meant to be one row, and then of data that you keep as one row. This is not available in the Visual Basic macro for Excel yet, but it is in the LibreOffice if you decide to use it. So it's something that I added to give you a bit more flexibility in what you can do with. For instance, we could have set record every 365 iterations, and so every year would have been recorded in our result. So this is how it works. I don't know what we will be able to accomplish today. Unfortunately, the connection seems to be very, very bad, and I just restarted the modem, so I'm not sure exactly what is going on. If it comes from the ISP or otherwise, it's very distracting. I'm really sorry about that. I'm not sure what is happening. So the next phase that I wanted to do was going to the 2D version of the problem that we had, right? So let me open the previous file that we had from last time, because I will need the 2D seepage for the next problem. So if we want to do 2D seepage, okay, so let me just copy. 2D consolidation, sorry, not 2D seepage. I will pause again. Let me restart again the modem, see if it does anything. My previous file, it was not seepage. It was the consolidation one. What was the name of the file? De momento, sí. Oh. Yes, an okay. Okay, so we go to this one, if I'm not mistaken. Nope. Just give me a second, I'll see if... did we disconnect again?
We have your voice, but we don't have.
Yeah, I know, I think it disconnected. Okay, give me a second. I will disconnect intentionally this time, just to see if I reset everything. Hopefully it does some good. Okay, I will disconnect and come back in a couple of minutes. Okay, hopefully this is a bit more stable without doing anything more drastic. Okay, so 1D consolidation. Oops. We still have this is defined as x, and this is defined as z within the scope of this sheet, right? What else is there that is not named? Q. Oh, Q. That was defined as Q. Oh, beta. No, beta and delta are sheet names. What is the name? Oh, it's still not working. trouble with these. Let me try something different. The names were not preserved for some reason, so okay. So if I reopen that file, save as. Okay. Hopefully that means I can open it. Okay. Now it seems to be okay. Let me just change the active window. No, I wanted to. So we'll just use the values from the previous sheet, so we avoid having too many complications. Okay, so I will create now a U-Naught sheet. So it's the stress distribution, but as we were saying earlier, the stress distribution, the pore pressure carries the change in total stress initially. And so we should be able to get from that the initial pore pressure, so that gives us our starting conditions basically. So if I paste paste as values, then I don't have to worry about what existed in the previous one. So this is our 2D stress distribution that we calculated in last lecture. Okay, so for a 1D problem, we just copied that first column when we did the 1D analysis. So that's what we put here as a horizontal value there. So this one I will call U-Naught, because that's the initial stress, or the initial pore pressures. And we have the X values and the Z values in this particular case. So I will add, oh my gosh, I think this time it may have worked. Well, I don't want to curse, I don't want to jinx it, but the way it was going, it was very distracting. So we call this pore pressure previous. Okay, the next sheet we will create is pore pressure next. Okay, just to keep, so we have two conditions. And with this method, we cannot, well, I suppose we could use matrices also, but we would have to reorganize all the data into simple columns instead of having in 2 by 2. So to be able to use matrix and use the implicit or Crank-Nicholson methods, we would have to, instead of having X and Z, we should have X, Y in 3 columns, X, Y, or X, Z, and then pore pressure. So we would have to remap that 2D grid into 3 columns. It's very doable. Just using the modulo function, you can remap things and then have very long queue, but then you would have to make an equally large matrix of how many points we have here. For this one, we have, if I look here at the bottom of my sheet, I have a count, average, minimum, sum. No, I want the count. 16,281. But I just want this. Yes. So 16,281 data points. So that's the number of rows we would have to have with 3 columns. Listing the X, the Z, and the excess pore pressure. Totally doable. But then you would need 16,000 by 16,000. I don't think I have 16,000 rows here, or columns available. So, but it's definitely something you could solve, say in Octave or MATLAB with a matrix. But again, that's the beauty of the implicit method, is that it does not require you to set up the space for that huge matrix. So you have a 16,000 by 16,000 matrix. Of course, for many of these problems, I think internally Octave and MATLAB are optimized, so it's a tri-diagonal matrix, right? So only the central diagonal has values, the 3 neighbors, and everything else is zeros basically in those matrices. So when those types of matrices are recognized, they optimize, so they don't store the full matrix in memory. However, when you invert them, you might still get numbers everywhere. So you would still have, in the inverted matrix, you might have to have all the components. So that being said, what we do here, to start one of these problems, we would go and copy and paste special as values into the previous set. Okay, I will do the same on the Unix, although this is mostly just to get my X and Y to orient myself. Because here I will change the boundary conditions. So now we have different boundary conditions, right? And as you will recall, we now have different sets of boundary conditions that we want to use. So what are the boundaries that we are interested in the problem if we want to solve it as a 2D problem? Well, we will want to define new sets of boundaries in this case, right? Because in the 1D problem we had no choice. We needed to have the double drainage, so the footing on top we ignored its effect because we assumed that this was a free draining, so we had one-dimensional problem. In 2D we can now, so we're looking at symmetry, we can assume that this entire zone here is no flow, and flow will be allowed elsewhere, and what we can say is outside of this boundary we will have 0 excess pore pressure. But then we have the center of symmetry. When you have a symmetrical problem like this, because things go the same way on both sides, we assume that we have an impervious barrier, right? Because the only way that to have symmetry, so if I have symmetry, it means that the pore pressure on this side at the same location is the same as the pore pressure on this side at the same location. And if the pore pressure is the same on both sides, there's nothing driving movement of water across that boundary. So that boundary has to be an impervious boundary. So this is a no-flow boundary when you have an axis of symmetry. In our case, we can also assume that at the bottom here we have 0 pore pressure. So excess pore pressure, it's free draining at the bottom. That's the assumption we made in 1D, and we'll keep the same assumption. So 0 pore pressure. And at the very end there, I mean, we could assume a specific, and we could say that it's also a zero pore pressure. Actually, it would be a good assumption for this particular type of problem, because water will be free to drain going that way also. It doesn't have to come all the way up. So we have added quite a bit of boundaries here, here, and there, and there. So instead of just having these two single points, and we can add the intricacies of what this gives us. But what will the equations look like to be able to solve this type of problem in 2D? Okay? So that's where the next file comes into play. And so we okay, so we have this one now. And so for 1D consolidation, the equation that we had was obviously the same we've been using for a while, since we started talking about Darcy's law, right? But we had expressed strain changes into excess pore pressure, and so we have the coefficient of consolidation there to tie everything up. When we have the change in volume, so we said that the change in volume is the change of water content. Again, oh, did we cut out again? Are you there still?
Yeah.
Yeah.
Okay, you're still seeing. Okay, because I got a Zoom message saying that, implying that we had cut out, but okay.
But sometimes you are breaking up.
Okay. I'm really sorry about that. We'll have to am I cutting up again?
No.
Oh, okay. I'm getting strange messages. So in terms of 3D, then the full 3D expression of Darcy's law was with the hydraulic conductivity in the x, y, and z directions. Each are independent, so the flow in one direction is independent of the flow in other directions. It just depends on the gradient of head in its own direction, right? But at the same time, the change in water content, so for a given volume, it doesn't matter if the water is going that way, or that way, so you add all the water leaving in all directions to tell you how much water you lost in any given area. That's why we add them all up into the that term. When we consider a 2D consolidation, we're neglecting the water that flows laterally. We're assuming that we have a very long scenario, which is the same everywhere. So the same thing as with symmetry, right? We said that when we have a symmetrical plane, the implication is that at a given depth, the pressure on this side and on that side, the excess pressure is the same. So if the pressure is the same, there can be no flow in that direction. Well, when you consider a 2D problem, a 2D problem is represented on a plane, but that plane is part of a volume that continues on both sides, right? But what it implies is that on this side here of the plane and on that side of the plane at a given depth, you have the same pressure on both sides, so there can be no flow in either direction because the loading is the same on a very long, so along a strip footing. That's the implication of 2D flow. When you're talking about stresses, you have two types of 2D problems you can have. so you have plane strain and plane stress. Plane stress means that you are allowed to, so in plane strain, the strain only occurs in the 2D, so you're confining with enough stress on the other side, on the perpendicular to your view, to the page, that no strain can occur there. Or you can have plane stress where there's no strain, no confinement, so you have no stress effectively going in the direction perpendicular. So it's important to define what type of problem you have and why it applies. But in case of 2D for consolidation, as in pore pressure dissipation, every case, it means that we have no flow basically in the y direction, considering that z is the vertical. So if this is the case, oops, then we can rewrite the equation like that, and therefore, following the same logic that we used last time, we can express it in terms of changes in excess pore pressure with a coefficient of consolidation that is different in the horizontal and vertical direction. Okay, so just following the same logic that we used last time. So this is the formula that we have to use this time to be able to solve our problem. Now, if we have isotropic material, so if it's isotropic, it will mean that CH is equal to CV. It's usually not the case, by the way, and particularly at the macro scale, because you average out the little inconsistencies and things are bedded. So usually consolidation occurs faster. You have more flow in the horizontal direction than in the vertical direction. Okay. So let's consider the same problem we had before, but this time we take into account 2D consolidation. Okay, and with 2D consolidation, we now have to set up our equations looking at the past, but now considering both directions. Okay, now things will change a little bit now. How does it look? So in the past, we had to worry about R in one direction only. Okay, now we have to redefine this, so we have to redevelop our equations the same way we did before. So we have now a coefficient of horizontal consolidation, and we have two space index. Instead of just being I, we have I and J. So I being in the X direction, J being in the Z direction, and then N is the index in time. Okay, that's what we're going for in this particular representation. So we have the same formula as before. We have delta X here, delta Z there, and our horizontal and vertical coefficients of consolidation. Delta T will be unique for the problem. So if we re-express everything, we have delta T that multiplies everything. So here we have an RH and here a RV. Okay. That can be replaced in there, and so the equation is basically the same as before. Okay, except now we have Rx and an R, or Rx and Rz in the mix. We still have one term of EUI. So the EUIs will be grouped. So we have minus 2RZ and minus 2. So 1 minus 2RX minus 2RZ. IJ, right? So that will be the expression. And so before we said that R had to be smaller or equal to 0.5, right? but that was really to say that 1 minus 2r must be larger or equal to 0. Okay, so that implies that 1 is larger or equal to, so 1 over 2 is larger or equal to r. In this case, the same general idea applies, but we have this term 1 minus 2 rx minus 2 rz, which must be larger or equal to 0. Okay? And that implies that so 1 is larger or equal to 2rx plus 2rz. So 1/2 is larger or equal to rx plus rz. So rx plus rz must be smaller or equal to 1/2. So the sum of the two r's must be smaller or equal to 1/2. Okay? That's the difference in this particular configuration than what we had before. Okay? So if r is constant because we have CV equals to CH, it means that 1 minus 4r, or r must be smaller or equal to 1/4. Okay? So always keep that in mind when setting up your problem. So by going 2 dimensions, we require for the same spatial resolution. So I needed 1.6 days before, was the largest time steps I could have. Now I need half of that, so less than a day will be required to properly represent my my domain. So if I do the calculation now, assuming our values. So what did we say? We said that CV was equal to 1.10 meters squared per year. We also said that delta x was equal to 0.1 meter, and delta z was equal to 0.1 meter. That means that Rx is equal, so in both cases we say CH equals CV. Okay, in this particular case we are still simplifying things, so it's still CV delta T over 0.1 meter squared, so delta x squared. And RZ meter squared per year times delta T. So let's see here that we use the one we had before, 1 over 365, and we say 0.1 meter. Okay, and both will be equal in this particular case. So just for fun, what does that give us? So 0.30136, 0.3. So that's good for now. It's the same value as before, except our condition has now changed, and we said that R must be smaller or equal to 1/4. Okay, that means 0.25, and that is larger than 0.25. So I can no longer use my 1 day as a benchmark. Okay, very important little detail, okay, that you should not miss. Okay, that R coefficient lets you tell many things in your problem. Now, as I said, in Crank-Nicholson and implicit method, you don't have to abide by the R, but calculating R even for those gives you a range of values or time step that you should not stray too far from if you want your values to remain meaningful, right? Because particularly the implicit method will not wobble the way the explicit method does, but the values that it gives you may not be realistic. Okay, this is still a good guide to know if your time step is too large for the spatial resolution that you have. Okay, so what you gain in spatial resolution, you now have to spend in more time steps. And so we're going to get to 10,000 iterations in this particular case instead of the 5,000 that we had to use before, just because of this. Okay, so we have now, so if I want to have something that is 1/4, so my delta t must be equal or smaller to 1/4 times delta x squared divided by CV, or 1/4 times 0.1 meter squared divided by 1.10 meter squared per year, which will give me, in terms of years, what do I get from that? I get 1/4 times 0.1 squared divided by 1.10. Okay, 0.0022, and if I multiply that by 365, that's about 0.8 days. I will use a half a day. So if we use a half day for delta t, it then means that our delta t would be, our R value will be 1.10 times 0.5 over 365 divided by 0.1 meter squared. Okay, so we have now R value of 0.15068. 0.15068 for 12 hours. Okay, for delta t equals 12 hours of playtime. So if we go with this into our calculations, we now have to go back to our sheet. So we can define a variable. Are you seeing the variables? You're not seeing the variables, are you? Okay. Let me make sure that I re-add that particular window. Spreadsheet. Manage names. There you go. Okay. So now we want to add oh no, we want to redefine R and we said that it should be 0.15068. Okay, so we have 0.15068. Oops. What was it before? I should have kept it. Before we said it was 0.5 times 0.1 squared divided by 1.10. No. Oh no, sorry. It was 1.10 times 1/365 divided by 0.1 square. Yes. 0.3013. Okay. For now, we'll keep this like that, and I will define a new variable called R2D, just to allow us to compare the two values, 0.15068. Okay. Because otherwise we would be changing the results of this 1D calculation. And if the objective later on will be to do some comparisons, then we want to be able to keep those. Okay, so we had the 1D here, and now we want to do it 2D, which means that now we can change. So we need to have our boundary conditions. Our boundary conditions will be zero pressure everywhere, excess pressure at the boundary, right? We do the same thing at this far right boundary and at the bottom boundary here. Okay. So those are boundary conditions that will drive all the changes. Then we have, so we can add the symmetry here by going to the values there. Okay. So that symmetry guarantees that we have the symmetry, central symmetry. And now here we can put our general equation with which was what was that equation? So here I want to make sure that that is included in here also. Okay, in the previous case. So equation was in the x direction, so let's go back to our okay, so we have Rx times the sum of the two neighbors in the x direction plus Rz times the sum of the neighbors and the z direction. But since Rx and Rz are the same in our particular case, we can just say it's equal to R2D times all the neighbors in the past tense plus 1 minus 4R times the same node in the previous case, right? So we can say it's R2D times from the previous one we go to all the neighbors. Plus 1 minus 4 times R2D times itself in the previous case. And that, in theory, is it. Okay. So now to run my little macro, what I have to do is redefine my variable called iteration source. And now iteration source will be this entire copied range, including the boundary condition. Okay. Because I will need to refer to that boundary with that formula. I could have changed the formula here to go twice on that side, but okay, so that would be another way of doing it to accommodate the boundary conditions. Okay, so I defined iteration source, and iteration target is the upper left corner of where I will paste it, and I will paste it there every time. Okay. So now we say OK. And now I can run my macro. Run macros. Iterative. Okay, so if I run my macros, how many? So if I want 15 years or 730, I can do 1 year at a time, for instance. So iterations, max iterations, we will say 365 times 2. So because I'm doing half a day, it means that to make 1 year, I need to have 2 times 365, right? So if I run my first set, my first year, okay, so I run it. I should have included my iteration indicator because now it becomes very difficult to know when we're done. Can I stop it? It can be difficult to stop. Okay, it's not too bad. It should come back to me shortly. Oh. It's still going. Yeah, iteration indicator is a good variable to define. You don't have to do it, but it lets you figure out how long you still have to wait. In the meantime, you have questions on what we've done here? That is a bit slow. So this is where actually using some programming language becomes faster, but you can still get the fun of using these little applications from time to time. Why do I have two sheets with the same? Whatever. Okay. I'm hearing... Oh, I believe I'm done. Yes, 730 iterations. So iterations indicator, I think it's a very valuable let me make sure how I called it. Tools, macros, edit. Iteration, yeah, indicator. And that's where it goes. So you just type in the little box there. Oops. So apparently I'm right on top of the box where I type things, so it's not very helpful for you guys. Okay. So I will call this cell iteration indicator. Good. And what we have here at Unix now is the first year, right? So I can insert a sheet, or the previous one is the one I want. I can make a copy, move to the end position, and port pressure 1 year. Okay, so I made a copy, and these are the copy pasted area, so they're all values, they're just numbers here, so I don't have the formulas, which will be for the next iteration. So this is 1 year that I have saved, and I can compare to initial condition. I made a mistake. Can you see my mistake? So we'll have to restart this because I did make a big mistake. My range was incorrectly oh, did I? Yeah, this should be previous. Prev. So I mislabeled my range in this particular case. And I did not keep, so these zeros are not pasted in the U previous, okay, because I mislabeled things. So it's good to go first with a smaller, say 10, just for fun, when you're in the test phase, and then you go to your full value later on. So what do we have here? And so we will copy this again, paste it to previous. Okay, and we change our boundary conditions there, constant boundary conditions. Okay, and and this is a mirror boundary for now. Okay, so that one is the proper U previous, and now we need to redefine the range because it should have started including the top row, right? So the name range iteration source should have been starting at B3, not B4. Okay, and iteration target, same thing, B3. So if I make just one iteration, macros, run macro in my iterative programming. Okay, just to make sure that everything is a-okay. Okay. Nope. Okay, so it was good that we did only one test. I think I did not properly save both. So we erase this, we say this is equal to the mirror. Okay. Verify our iteration ranges. Iteration source, it's from B3 iteration source B3 to GU83. GU, okay. And iteration target is indeed B3. Okay. Now again, we try one iteration. Running the macros, macro run. Okay, that was perfect. So if I want to complete 1 year, I just go back here, say 729, because I already did one iteration, so I don't want to just repeat that one. And I can run for the rest of my year, run my little iteration. So I do macro, tools, macro, run macro. I can also add a shortcut, which I will do next time. So once in a while, this iteration indicator should be updated. I should probably also have a little progress bar, but that's something I can add later on. It's little things that are very convenient, although they add also a little bit of, so 96. So once in a while it will be updated and we'll see. It is being updated continuously, but because of the number of operations that are being done, the screen, the image is not updated all the time to save on, that's built into the software to save on processing time. So while that goes on, any questions? So we won't do 15 years so far. I can finish that comparison separately and upload the resulting file. But you can see right away that it gives you a different flavor from the 1D consolidations that we were running until now. No questions? You can still hear me, right?
Yeah, we can hear you.
Oh, okay, thank you. Okay, we should be progressing. So we need to go to about 10,000 iterations for, I mean, it's not a big deal. We could run this if we set it up, do a few tests, we go have dinner, and we come back and the calculations are done, and we have a pore pressure distribution. You could do that for a slope. You can do like if you want to evaluate the time rate of flow of water, you could set also up that kind of problem. And again, these things go less fast than a spreadsheet typically. Although I must say that LibreOffice, if you have a good computer with a good GPU, LibreOffice is able to use GPUs to significantly improve performance, because GPU is in your graphics card. You basically have little processors, and each processor, so you can do parallel programming, and spreadsheets are very good at that. So each of these cells, each of these small calculations is actually pretty good, because you just go and do a calculation and you can break up each cell, so you can separate a group of cells to one processor and another one to another, and because they look at the past tense, it's not a matrix to solve, right? So this type of calculation using the explicit finite difference is very good for parallel processing. Matrix inversions, so if you want to solve finite element or the implicit method or Crank-Nicolson method in finite difference, you have to solve the matrix, which is less good because things are interrelated. You need to look up at all your numbers, so you can less do individual calculations. But this types of calculation that we do with the explicit finite difference is extremely parallelizable. Okay, so you see each cell just refers to a previous data set independently from what the other cells are calculating in the same row, and so you don't need to wait for the result of one calculations to be able to do the next one, right? So each cell can do its own calculations without waiting for the neighbor cell to have finished its own calculations. Okay, if it makes any sense. So this entire process would be sped up significantly. So now I can make a copy, this time correctly, by making sure I select make a copy. I move to the end position and I call it 1 year. Okay, so now we have a new tab that's called do 1 year. And if I wanted to do my next year, then I would just set that to 730. And I will definitely do that, but we don't need to do it right now. Let's proceed with the rest of the lesson. So now we saw what a 2D analysis entails. And you remember, a 2D analysis entails that you have things extended to infinity perpendicular to your image. Okay, perpendicular to the screen, it goes to infinity. Okay, or very long anyway. So it's good for strip footings, problems of that sort. But it would not be a good representation of a circular footing or a square footing. For square footing, you need to go all the way to 3D. For something like a circular footing or anything that is circular, symmetric in all directions, you can actually kind of still use 2D, but you tweak it a little bit. So you're cheating basically. You're saying, well, it's the same way in all directions. Remember, that doesn't work if you have a specific condition on site where there's flow of water in a specific direction because of the local geometry. This works only if everything is symmetrical in all directions. Okay, and therefore you can do 2D to really represent a 3D scenario. So okay, this is just the solution of this specific problems. If we go with the number of days from 0 days to 90 days, I did 365, but this is what you would get in terms of pore pressure dissipations in this particular case. Or if you represent it in terms of depth for 0 days, 5 days, okay, these are the kind of figures you could generate. Okay, I will let you work it out. But we're going to consider now the setting up of problems for axisymmetric flow equations. And these assume that everything is symmetrical with respect to a center. So you can do 2D, but it's really 3D because it's the same way in all directions. Okay, so when you have a circular loading condition, it's symmetrical in all directions. So you can definitely use this, particularly if there's no change. Of course, it only works with perfectly horizontal soil layers. Otherwise, you would, if you have any change in geometry, it would have to be like a conical change in geometry that's the same going towards the center. Okay, so that's the limitation of this. But it is kind of a fake 3D. And again, we go with the change in water content. But this time, our integration element is different. Okay, so the volume change, it's the volume so the change of water content over time is equal to the change in volume of water over time over the overall volume, right? So change of volume over volume, that's the change of water content. So change of volume over T, that's dq over T over volume. That gives you the same kind of problem solution. So what is the volume of a sector of a cylinder? Well, you have del of z, del of theta, that's the angular, that's not the water content in this case, but it's really the angular, it's the angle of the little sector, and the increment of radius along the radius, right? So we want a point somewhere in the middle. So at the middle of that sector we have radius r. Okay, so we take just a little segment out of our entire cylinder. Okay, a little element. But what's key is that the outside edge is longer than the inside edge. And the volume of a sector is what? Is r d theta. That gives us the length of the arc. And so we assume equal in all directions, but each element will be smaller. So times dr times dz. Okay, so this length, r d theta times dr times dz, gives us a little cube, essentially. The area coming in is r minus half of dr, d theta dz. So that's the area in. The area of water going out is r plus half dr d theta dz. Okay, so that's just the area on the inside and on the outside. Okay? And it's important because to get the same volume of water coming in as going out, because the area on the closer to the center of symmetry is smaller than outside, that means that you need a higher flux, a higher Darcy flux Qx coming in compared to going out for no storage. Okay, for steady state, you need to have higher flow in, and then it goes into a bigger area, so it becomes less and less and less flux for a given amount of water coming in and going out. So basically the flow going in is QNAN, and so you just substitute that into your equations. Okay, and you end up with the Q, the Darcy flux in the radial direction is minus K d theta dH over dr. But you also have an element, okay, so in the Z direction. Okay, so the change in water content is delta over Q over dr minus QR dr. Okay, that's just by developing the equation, because it's R in minus R out, which is the volume that increases into the volume. Okay, and so expanding the other term is easy. So this one is only like we saw before. This part is like we saw before, but where it's different is that we have delta H over del R, which is not squared, you notice, and it's inversely proportional to the radius. Okay. So if we have a heterogeneous material and non-isotropic, so Kr and Kz will be different, but we have to keep it also in to the equation so that we can deal with different soils. So the next example that we want to solve will be using a 1 meter diameter well that we dug in the clay layer, which is 8 meter thick, and it has an isotropic hydraulic conductivity of 5 times 10 to the minus 8 meter cube per meter squared second. Okay? So meter per second. So find the hydraulic head within the clay layer at steady state. So if we have a question that is at steady state, we can also solve it using these types of equation in an axisymmetric problem. Okay. So we have two particular questions here to consider in this example that is provided. First is that we must assume that the well is dug to the impervious bedrock, which is below the soil, below the surface, or stop the well at 3 meters depth. So to solve this kind of problem, we go back to our equation, but it's steady state, so change in water content over time must equal to 0. So if we set that as our problem, and we know that the soil is uniform and isotropic, so this is a constant in this particular case. So they're both equal to each other, and because it's uniform, they're also constant. So we can reduce the equation to a simpler form, so we get rid of the k's in both cases. Okay. And so we expand the equations the way we did before. So the del square h over del r becomes delta r squared at the denominator. Numerator, it's h minus 2h plus h. But here in this term, it's only del h. So del h is the two neighbors. Okay? And because it's the two neighbors, okay, I take this minus that. The distance between them is not delta r, but it's 2 delta r. That's why we have 2 delta r there. Okay? So 1 r times a difference in neighbors over 2 delta r. And the other one is like we have done before. Okay, so this little pattern is one that you should remember. It comes on very often in these kind of math, and it's from that equation. Okay. So now we can regroup our materials, so we don't necessarily have the same spacing in the radial and the vertical direction. Okay, but we can regroup Hij terms and the terms that are on the neighbors in this way. Okay, and so we can isolate for the node value based on the neighboring cells. Okay, so we just refer to the neighbors, and we see that we still need to keep the radius there. It's not just the delta r, but there's one term here that will vary based on our distance from the center of symmetry. Okay, so I will stop here. I think next time we'll see how to how this looks, as well as axisymmetric consolidation, where we will use we will solve a problem that is comparable to the one that we've seen today in 2D. But this time we will consider a circular foundation with the same loads. So the same load, the same thickness, but this time the problem will be axisymmetric, so it's not purely 2D. Okay, so that being said, are there any questions? Okay, if there are no questions, I invite you to explore the macros that I have made available. Oh, let me, before I completely close in, let me see if I can actually see them right now, because the internet seems to be working much better now. So can I log into Student Labs? I still cannot, apparently. I just wanted to give you a quick show of how to install it in Excel if that's what you're using, or also in a copy of LibreOffice that doesn't have it, but I think I will have to wait and just record a separate video with that. Yes, I'm still not connecting. Anyways, are there any questions? So if there are no questions, I think we'll cut it here. Over the weekend, I will try to post that video on the installation of the macros and running the macros, because you can see that being able to perform iterations on a spreadsheet can make it very useful. And you can skip sometimes the programming and programming language that you may not be familiar with. And so for prototyping, it's good. I mean, programming is always better to do the hard work, but spreadsheets are awesome for prototyping. No questions? No comments? In that case, I will say good night, and I will see you next time.
Could you please
Oh,
update
yes.
the Excel that?
Yes, I will definitely do that.
Thank you. Thank you.
No problem. Good night. Take care.
Bye, Professor.